My crystals have grown a lot since the last video. The seeds of nucleation have grown to form larger crystals, and the solvent level, the liquid, in the vial is noticeably lower, meaning that a lot of the solvent has evaporated. There are some environmental factors that could be affecting the growth of my crystals right now. One big influence is the recent weather. Since the huge cold spell throughout the Midwest, my room has been extremely cold, despite the fact that all our windows are closed completely. Um, and a decrease in temperature has the potential to decrease the rate of formation of my crystals, and this is because with a colder temperature, the rate of evaporation decreases. The kinetic energy of the solvent molecules experiences a net decrease, which is the reason behind the decrease in the rate of evaporation. But besides the temperature, there shouldn't have been any other significant environmental factors, and the crystals have been kept in a relatively dark location without much disturbance from vibrations or anything else. And so when calculating the theoretical yield for my product, I first wrote out all the balanced equations for the series of reactions from Professor Nez's lab introduction and my pre-lab. And so they're right here. But looking at the series of equations, the mole ratio of initial aluminum to alum at the end, right here, and aluminum right here, the mole ratio is 1:1, which is emphasized by all the red boxes that are drawn around the aluminum-based intermediates that eventually result in the production of alum. Therefore, to calculate the theoretical yield of alum in terms of mass, which is shown down here, I first had to convert the initial mass of aluminum to moles of aluminum using the molar mass of aluminum, which is 26 atomic mass units. Then using a conversion factor, that 1 mole of alum is equal to 1 mole of aluminum, I was able to convert to moles of alum. And then finally using the molar mass of alum, which is 474.372 AMUs, I converted moles of alum to the theoretical yield in terms of mass based solely on the initial mass of aluminum, and that value was calculated to be approximately 17.8 grams of alum, which is shown right there. And so with this theoretical yield, I can calculate the percent yield, which is shown right here, number 3. So the experimental yield of alum was measured to be 5.60 grams. And to calculate the percent yield, I just used the formula experimental value over theoretical value multiplied by a factor of 100. And substituting my values into the equation, 5.60 grams of alum over 17.8 grams of alum times 100, my percent yield ended up being about 31.5%. So my percent yield is clearly not 100%. And initially the value seemed extremely low to me. However, after thinking about my laboratory process, I realized that there are many reasons for such a low percent yield. For instance, one reason could be that the aluminum foil was not comprised of pure aluminum. For instance, many sheets of aluminum foil are not pure aluminum and are coated with aluminum oxide or plastics or something of the sort. And this was this was further suggested by the fact that impurities had to be filtered out of the solution after the aluminum was mixed with the KOH and water solution. Furthermore, it is possible that the ice bath did not induce a large enough temperature decrease to precipitate all of the alum from the solution. And when we put the solution on an ice bath, it did take a very long time for us to notice a precipitate. Lastly, it's very possible that some of the crystallized alum was left on the bottom or sides of the beaker that the solution was in before it was filtered. To prevent this kind of error in the future, the group members should make sure to get all of the desired product from the container, and in this case that could have been done by rinsing the beaker with the 50-50 ethanol water mixture and pouring this into the Buckner funnel, because in that way the alum would not have been dissolved and would have been preserved, but still we would have been able to get it out of the beaker.